I'm John Hart from the Mechanical Engineering Department, and I have the privilege of chairing this next session on manufacturing. And as I was sitting at the back preparing, I realized this is a bit of a full circle moment because while I was doing my master's and PhD in mechanical engineering here, I transitioned between degrees from focusing on machine design, precision engineering, to an unexpected focus on nanomaterials, which led me to spend long days with a first-generation iPod hidden in my clean room suit in the MTL, the precursor to MIT.nano, and the convergence of those two topics shaped the first decade or so of my faculty career. So after I give some introductory remarks, I'll introduce our outstanding speakers who will also span the spectrum of manufacturing in some ways from the inside MIT perspective and also from the outside MIT perspective, or what we like to see MIT's impact in manufacturing to be beyond the borders of our campus. I came to MIT about 12 years ago. There we go. And since then, I've seen an incredible growth in manufacturing across campus. We've already heard some outstanding remarks connecting manufacturing to health and life sciences, and in the opening by Vladimir and Sally before that. But along with the growth of manufacturing across disciplines at MIT, it really is in MIT's DNA. We have manufacturing in all engineering departments, in humanities and social sciences, of course in management and operations, and MIT's dedication to manufacturing, part of its industrial inspiration and mind-in-hand ethos, is not only about technology, research and education, but it's also about understanding the landscape of manufacturing domestically and globally, and it's about getting people out of campus, our graduates, who are budding enthusiasts of manufacturing, and when the opportunity presents itself, starting and scaling new companies. So collecting these like terms, so to say, we're very proud that alongside, I'm sorry, I don't think the remote is working, but if you can advance the next slide, alongside HEALS and the other strategic initiatives, MIT launched in May the MIT Initiative for New Manufacturing, or INM. I have the privilege of being one of the faculty co-directors, along with Professor Suzanne Berger and Professor Chris Love. Suzanne, an institute professor of political science, and Chris, a professor of chemical engineering, an expert in biomanufacturing, and Rick Locke, dean of the Sloan School, and Paula Hammond, institute professor and executive vice provost, are the co-chairs of our steering committee. And the INM, by definition, as one of these strategic initiatives, has broad goals. Goals to unite MIT in manufacturing and support research, education, and partnerships to improve manufacturing in the US and across the world. We're just getting started. We've only been live for about 6 months, but we have defined 4 cross-cutting themes that define MIT's work across campus and with its partners. Reimagining manufacturing technologies and systems, elevating the productivity and experience of manufacturing, which really speaks to the human nature of manufacturing and how work and worker productivity are key to the frontier. Scaling new manufacturing, working internally and externally with young companies and old companies to understand and help them go from one to many, the true beauty of what makes manufacturing magical and mysterious, and transforming the manufacturing base, speaking to working with not just big companies, but small and medium enterprises, particularly from the workforce education side, as John Liu will speak in particular in a little while. We've identified several program areas, areas of focus activity, supporting research in manufacturing across MIT, both in technology domains and cross-cutting themes, focusing on deployment, taking MIT's work outside of campus through workforce training, through visiting small and medium enterprises, and so on. Alongside of those, a deep focus on education and workforce on campus and beyond, supporting new laboratories as we raise funding and build programs around campus, including a partnership we've already established with MIT.nano in the area of 3D printing. We're engaging industry through a consortium of large companies, and we are ideating programs in collaboration with the Trust Center, Deshpande Center, and others to focus on manufacturing entrepreneurship. The I&M started by an organic process, a community that we gathered to say, hey, how broad and how important is manufacturing? How exciting is it to our community? And this has included early efforts on workforce training, like Manufacturing Academy piloted in the Berkshires in Western Massachusetts. A series of amazing distinguished speakers like Morris Chang, October of 2 years ago, who filled 10250 and has such an incredible story to tell about his career in the semiconductor industry. And as I mentioned, efforts, particularly here supported by the Mass Tech Collaborative, to put new manufacturing equipment at MIT, specifically in a lab provided in partnership with MIT.nano on the 5th floor, and some space in mechanical engineering aside of our other manufacturing courses. And we're also proud to have 7 founding industry members of our consortium. The industry consortium is only one part of the initiative, but a key part. And we're engaging closely with those companies and open to new introductions at any time. And last but not least, more of a note for our on-campus audience, we have just opened up a call for I&M's first set of seed research projects, here focused on AI and automation for manufacturing. It's a top interest of our industry members, which is the source of funding supporting this seed call. And while we'll have hopefully many calls for proposals that stretch across all the different domains I highlighted, this one is focused on a set of topics related to AI and automation. If you are interested, please see our website or go to inm.mit.edu and click the tab on Request for Proposals, and we'll be able to fund 7 to 10 projects, both as research projects and demonstration projects to help translate capabilities already developed on campus into industry contexts. So with that, let me transition to our set of speakers. Leading off will be Dan Oran, who's a MIT PhD. I first met him when he was finishing up his PhD and thinking about starting the company that is incredibly exciting called Irradiant Technologies. After Dan, we'll hear from Professor Liz Reynolds, a professor of practice in the Department of Urban Studies and Planning, but her expertise stretches far beyond just being a professor at MIT, including a key role in the White House in the Biden administration, and John Liu, principal research scientist in mechanical engineering, who will speak about his innovative work and innovative deployment of new pedagogy for manufacturing workforce education. Each will have a brief presentation with some slides, and then I think we'll have time for a panel discussion and any questions that you submit through the pigeonhole back there. So Dan, please come on up.
So I'm here to tell you a little bit about Irradiant Technologies, and just to give you a little bit of context here, what we're all about is that we think 3D nanofabrication is what's going to fully unlock the potential of optics and photonics. And, you know, that all started with some very simple questions quite some time ago about what actually is necessary in order to do first principles 3D nanofabrication that is not just practical, but pragmatic and which can scale. So this has brought us to where we are now, where we're building the world's first 3D nano optics and photonics foundry. And we're able to pattern any arbitrary geometry. We're able to do that with deeply sub-wavelength resolution. And not only that, but we can control gradients of material and achieve things like gradients of refractive index. And most importantly, we're able to do it with materials that are compatible with existing foundry technologies. Now, further into the future, you can even imagine using this technique to do multi-material. We've shown it's possible to do conductors, semiconductors, and dielectrics all at once. But in practice, none of this actually matters, because there did not exist a way to do 3D nanofabrication fast enough. So of course, we also had to go and invent that here at MIT with Peter So, something called line scan temporally focused two-photon lithography, which is a big mouthful. But the point is here that this allows you to, instead of scanning a single point, pattern entire planes, and that means you can go fast enough for this to be economically feasible and make millions of components per year per customer. And with that, we've shown we can make everything from lenses for coupling, imaging, and relaying to things like filters for mux, demux, and compute, as well as 3D waveguides and reflectors for routing, as well as mux and demux. But that's just these subcomponents. Really, this is a transition, one that looks a lot like what happened with the transistor, where we went from soldering these parts together to then creating entire integrated systems out of them, but being able to do that for free space optics and photonics. So that's a little bit about the company, but it wasn't such a simple path to get here. I actually started out as an artist and photographer. I ran a printmaking business and an art business, sort of exploring what's possible with sculpting light. And it just so happened that one of my best friends had started here at MIT, and over some beers at the Miracle of Science, we realized we could combine these very old photographic printmaking technologies with new tools from neuroscience. And that's where this all started, essentially. We tried some stuff in lab. I got adopted by a professor at Boyden, became a technician, a master's student, and then got a PhD, published in Science magazine, then spun this out via the Activate Fellowship, which supports scientists to bring their ideas and research to market. And then, even then, it was still early. There was scientific risk left to be dealt with, so we raised money from the government through SBIRs. We then took that and we showed we could make high quality optical materials. And with that out of the way, we were able to go raise our seed round. We won a DARPA program. And with that DARPA program, we've been able to grow to now 30 people. We have a facility here in Waltham where we're now building the world's first 3D fabrication foundry. And that's where we are today. And finally, customers are taking us seriously. We're doing development deals with them, and hopefully in a few years, we'll have a scaled manufacturing facility that'll allow us to make millions of components for AI hyperscalers. Specifically, the beachhead that we found is in connectors for data centers. This is a major issue, just shifting from using copper to connect chips and things within racks together to using light. But further in the future, what we imagine is actually being able to shift the substrate for computation completely away or partially away from electrons to photons, and enable new kinds of sensors that allow embodied intelligence to essentially navigate and understand our world. So with that, I'll let the other folks come up, and thank you very much.
Great. Well, good morning, everyone. It's a real pleasure to be here, and particularly with old and dear colleagues from many years working on the topic of advanced manufacturing and policy, et cetera. My name is Liz Reynolds, and as John alluded, I have been involved in advanced manufacturing topics at MIT for over a decade now. But what's been interesting in the last 5 years or so is to see how much this topic has become critical, not just in the US, but around the world. And the movement, the sort of headwinds and tailwinds that are working right now in rebuilding advanced manufacturing bases and reindustrializing is really quite fascinating. And I think we could all probably say the next 5 to 10 years will be the most dynamic time that we've been in when it comes to thinking about advanced manufacturing and society more broadly. So I'm just going to I'm sort of doing a 60,000 feet view on what's been going on, and I apologize for this parochial view, which is a US-centric view. I did work for the Biden administration, and I am grounded in some of the views on that front, but they are evolving, as I'll talk about, and hopefully this also sets the stage for what John is going to say. So let me first by just talking about what are the motivators behind this movement and what many have been calling sort of the next industrial revolution. And I think I'm going to list 4 here, and we'll talk more broadly, I think, about others throughout the day. But people can first and foremost, I think it was the global pandemic that essentially highlighted all the vulnerabilities in the US economy vis-a-vis manufacturing and resilience in our supply chains domestically, and also globally. But whether it was from personal protective equipment to semiconductors, everyone's quite aware of that, we had significant challenges for the country, and they affected not just national security, but economic security, which now it's really hard to say where does one start and where does one finish. But for semiconductors, many will remember that when we had the shortage of semiconductors in 2021, the auto industry essentially shut down, and that directly affected inflation that year by a third. And so you're seeing this interaction of the issues that were both for national security purposes but also economic security purposes a real problem. Climate change, climate change now tends to be discussed in terms of energy security, but we have increasing threats due to climate change, but we're also seeing, as the demands from AI increase and from increasing manufacturing centers as well, that companies are thinking about energy security in a different way. And that requires integrating both their manufacturing and their data requirements in space, in sort of places. Do we have enough energy? Do we have enough water? Do we have enough capabilities basically to drive our industrial or reindustrialization? Third, the geopolitical landscape, of course. We've seen with Russia's invasion of Ukraine and other conflicts, first and foremost, a real stress on the U.S. defense industrial base, challenges to actually supplying enough ammunition, legacy systems that are not rising to the challenge. And then, of course, the tension that's been growing with China over both military challenges but also technological challenges. And there's data now to suggest that the U.S. has fallen behind China in many critical areas. Finally, inequality. This is, I think, at the core of a lot of our challenges sort of socially around democracy. It's not just happening in the US, it's happening everywhere, but economic populism is often grounded in economic insecurity. And so the manufacturing agenda actually has been, an area where people feel there is an opportunity for expanding middle-class jobs, et cetera. But that, in my mind, is also a motivator for a lot of the policy we've been seeing. So I want to talk a little bit about MIT's response. I don't know if I'd call it, I think I'd call it a response to a lot of what's going on, which is Simon Johnson and I, a couple years ago, started a priority technologies seminar. And the idea here was that what we see is a real convergence of technological developments, frontier technology, innovation going on both at the firm and national level, and policy interests. And these are converging to sort of try and meet this moment of national and economic security challenges for the US. And so we've developed a seminar. We've had a number of our faculty present on areas where they are leaning in to the technology development, but also where there's significant policy implications. What does it mean for the country, for the US and also around the world, to move forward and to advance in these particular areas? Of course, semiconductors is one of the key areas, since we've seen the challenge and then the introduction of the CHIPS Act by the Biden administration a few years ago. And I think they also, there's 6 areas which reflect, in some ways, foundational technologies like critical minerals and semiconductors, or foundational areas really in the upstream value chain, to frontier technologies, biomanufacturing, quantum, to some of the downstream important work in advanced manufacturing and drones really as a case study. This is not, of course, an exhaustive list, but a list that is evocative of what the challenges are for the country in combining both our innovation ecosystem with our industrial ecosystem. And how do those two interact? I think drones are a great example of that, where obviously very dependent on critical minerals supply, on semiconductors, on advanced manufacturing technologies, and on the ability to actually make drones at scale. Right now in the US, we make about 100,000 a year. That needs to be expanded to about 1 million plus a year. And how are we going to do that? Where are we going to do that? Those are important questions right now. And just to highlight a couple of the cross-cutting themes, workforce, which John will be talking about, comes up all the time across each one of these critical areas about, does the US have, both at a technician level and at a higher education level, the workforce it needs? And I feel like Vlad has been leading the charge on what universities need to be doing and could be doing to help educate the next generation. Supply chains and manufacturing, as I mentioned, without a secure supply chain, The U.S. is really vulnerable in a lot of these areas, and we have to be looking ahead in that area. We're quite behind, of course, in critical minerals. But as you look at quantum, for example, how do we build in resilience across not just the country, but with allies and partners? Scale up and demand pull. This issue of, and we heard it earlier with some of the panelists, but how are companies like Dan's making the move from the lab to, and prototypes, to the pilot production, to demonstration, to commercialization. The U.S. capital markets has not historically been well organized for that kind of support, particularly in growth capital. So what are we seeing there, and what's the role of government and the federal government to provide some of that demand early on? Small and medium-sized firms, we have a challenge with adopting new technology, not just the invention of the technology, but the adoption of the technology, which has always been a challenge, or is perhaps part of the technology life cycle, which often takes about 30 years to really play out. And then finally, R&D, and I think this is particularly important given what we see in the country right now, is without that continued support by the federal government, which goes to universities and elsewhere, we will have challenges breaking through into new technologies. We'll have challenges leapfrogging in existing places. So the R&D is a critical part of the U.S. innovation ecosystem. So this is a book coming out next spring, and I think that it's really helpful, and the lessons that come out of this can really inform directions going forward for the U.S. and beyond. But let me just take a quick moment to talk about this industrial strategy that I think we are now fully part of in the U.S. And again, as I mentioned before, what we see is that industrial strategy and policy usually steps in when we see markets are not responding to what we need sort of through a national security lens or an economic security lens. That became clear with the Biden administration on semiconductors, on critical minerals, on our defense industrial base, places where we need a government to step in. And what's interesting is to see that in this current administration, we're seeing likewise an agreement and an investment in some of these areas, a focus on resilience, a focus on reindustrialization, a focus on foreign direct investment as a priority, but also a focus on America First, which brings its own challenges. And I just wanted to highlight, I think people may be familiar, but some of these are really kind of interesting new directions that the US government is taking, which is very active steps in investing in companies to strengthen our supply chains and perhaps create what some might call national champions, which has pros and cons. But the MP Materials deal, where the Biden administration had invested in MP Materials, now DoD, largest stakeholder, very actively trying to build and create opportunities or capabilities in magnet manufacturing. The Intel deal, grants that were given by the Biden administration, now equity investments, now an equity stake, and the deal with NVIDIA, which was counter to the national security interest that the Biden administration had outlined. Also, just very novel ways in which the government is moving forward. Nippon Steel, again, trying to secure domestic production capabilities long term. So continuity and divergence, I'm just going to talk a bit in terms of the continuity between the last administration and this administration, U.S. policy. A lot of similarities in terms of the focus on industries. Again, critical minerals, semiconductors, and the semiconductor piece, I think, for this group might be particularly interesting. As we know, there's been a lot of investment in building capabilities for frontier manufacturing in the country. But right now, what we're seeing also is a pulling back on some of the R&D investments, some of the investments in packaging capabilities, and creating more of a broad fund for supporting many different types of projects and companies. There's an agreement that really internationally, the World Trade Organization policies have not served the country well, unfair trade practices that people want to change that model. And then the response to China, we can debate about the use of tariffs and how they're used, but certainly this idea that the US needs to be strengthening its relationship vis-a-vis technological development with China. And then differences, I won't go into these in great detail, but I think people probably are aware of the tariff tariffs now that are broad-based and I think are creating a headwind for U.S. manufacturing right now in terms of increasing the intermediate costs of a lot of manufacturing. The administration is sort of picking winners. It's not to say that these companies aren't worthy of investment, but it doesn't have the competitive process that you might see to help build industries that are globally competitive. It's also focused on FDI. And then I think it's fair to say that there is an undermining, given the investment challenges that we're seeing, or the pulling back of investment from a lot of the national agencies in science and technology, that will have challenges for the country long term. So to that, let me just say the broader implications. I'll just close on a couple thoughts that hopefully are food for discussion. I think that we have concerns now about what are the long-term impacts on U.S. leadership and technology and science if our R&D engine is compromised. That was discussed, I think, maybe touched upon in the last panel, but a real issue there. We are also seeing, I think, allies and partners turning in other directions in terms of their investments and their partnerships, a risk of U.S. isolationism and greater protectionism that will be problematic. Limited state capacity in that we are seeing both a reduction in workforce today, particularly in the federal government, lack of capacity really to deliver on some of the agenda items that I mentioned earlier for manufacturing, and more of a focus on deals, one-on-one deals with different companies. And I like to say everything's on the table all the time, that there's a lot of dynamic engagement right now in all that's going on and trying to rebuild the industrial base in the U.S. I'm happy, I would say, in the semiconductor space. I think there's more continuity. There's less pulling back on some of the investments that have been made. But investing in the R&D piece is critical, and it's unclear what that's going to look like going forward. So with that, I'll stop and hand over to John. Thank you.
Okay. Hello, everyone. I'm John Liu. I teach in the mechanical engineering department here, and I lead a group in learning engineering. So what I want to talk about is, these are the kinds of headlines that certainly might have caught your eyes, certainly catch my eyes. For example, Apple about half a year ago announced $500 billion to expand manufacturing operations in the US, and then last month changed that number to 600. Usually these numbers are across, 1-2 decades. This number is across 4 years. GE Vernova is making huge investments. Rivian just announced last week that they're breaking ground in their $5 billion plant. These are not just one-offs as well. There's actually a ton of different $1 billion projects. This graphic just came out a few months ago. All the $1 billion projects happening, breaking ground across the US, and they all come, of course, with hundreds and thousands of jobs. Also, not just one, sites here and there. If you take a look at what are manufacturing firms actually struggling with, though? I mean, certainly a lot of very positive investment into it. These are quarterly surveys done by National Association of Manufacturing. Basically, what's your top pain point? Is it business? Is it the economy and sales? What I want to point out is that the gray has been rising, and in fact, other than a small gap in COVID, it's really been at the top for the past few years. What's gray? Gray is attracting and retaining a quality workforce, and so gray has been king for the past 4 or 5 years. And it's not just showing up in employer perceptions, it's also in our demographic data as well. So what you're seeing in the red is demographics of the manufacturing workforce about 20 years ago. And what you're seeing on the horizontal axis, again, is age. So there's been a massive shift of age to the right. So blue is where we're at now in the recent years. Manufacturing workforce now, Bureau of Labor Statistics basically estimates about 25% over 55 and above. So essentially what we're seeing is a very, very large, that peak there, a huge wave of retirements in the next decade. And so this story in the US is not just a US story. You'll hear this, and I was just in Europe recently. They're also struggling with a similar issue. India also wants to grow out their manufacturing workforce. We have projects there as well. And so these are some of the questions I'm really interested in asking. possibilities for new good jobs, how are requirements changing, how do we prepare industries and people for them, new systems and tools to develop how we and transform how we learn and how we work in STEM, and then finally, what kinds of fundamental knowledge do we have to uncover about how humans work and learn in these kinds of industries. So 2 years ago, we were 3 people. Now this is a picture just from a few weeks ago. Really people from the background, 3 kinds of backgrounds in my group: human machine, computer interaction, XR, learning sciences, education, and then straight up mechanical engineering, manufacturing. That's kind of the 3 kind of buckets of knowledge that we generally draw from. So what I want to do now is kind of look through or kind of give you a survey of some of the projects that we've been able to do, and hopefully they'll be relevant to this audience. The first one is all the way on the system side. So when we think about advanced manufacturing, I have a premise or a hypothesis that, hey, we believe there's something that's holding people back in the workforce, and that is there's a kind of a gap between what technicians do and know and what engineers do and know. And in fact, when we've interviewed now scores of firms, we kind of hear a mantra like, hey, I wish engineers had hands-on skills. But I wish technicians had analytical skills. And we believe that in order to adopt and integrate new technologies, these new technologies are all connected. So you can't just bring in a new machine and expect that to work. It has upstream and downstream effects. Technologies like IoT or robotics or many of the digital technologies as well. And so the question is, what kind of worker really needs to be able to do this? We started to ask a few years ago, maybe we're thinking about this in the wrong way. Perhaps we really need a new worker type. And so this project, which we've now published last year in National Academy's policy-facing journal, is about proposing a new type of worker to help firms move into advanced manufacturing. I'm calling this worker the technologist. And what we're doing essentially is creating a bridge to collaborate both with the technicians who know the processes and the equipment very well, and the engineers who are making decisions on the level of design all the way to systems and operations. And so this is essentially we're taking and drawing from the core of curriculum that we teach here at MIT, the Masters of Engineering and Advanced Manufacturing Design, and adapting it for a new audience, folks without university degrees, folks who are assemblers, operators, technicians on the factory floor. So far, we've been targeting aerospace, defense, marine, industrial base, but now we're in conversations with Applied Materials, Samsung, thinking about how do we bridge over to the semiconductor industry. I'm pleased to share we're just about to finish round 1, phase 1 funding from the DoD, and we just were awarded a $5.5 million grant to disseminate to 6 sites in New England, targeting against the aerospace, defense, and marine industrial base. So the 6 sites, 2 in Rhode Island, 3 in Massachusetts, 1 in Connecticut. Even though the numbers are small, we're promising to educate about 180 technologists over the next 2 years. But we ended up receiving letters of support from senators from all 3 states, primarily because of the potential economic impact that it would have on states and helping industries regain competitiveness. So that's an example of the kinds of work that we do on whole manufacturing workforce systems or workforce training systems. Now I want to spend a little bit of time just highlighting some of the kind of when we think about individuals learning, what kinds of technologies might we be able to develop to support that kind of learning as well. Okay, so here's an example. Obviously, a lot of work in VR training these days. We have a paper coming out where we're benchmarking a lot of that VR training, especially targeting towards manufacturing. Turns out, I can say kind of one of the key takeaways. We don't believe that a lot of this is informed by learning theories and learning sciences. So what we're trying to do is to try to push up against the space. Hey, how do the learning theories and learning sciences from education inform the design of these environments? So we've now developed a kind of a demo environment where now you can learn by making mistakes and making meaning of your decisions and choices, where the environment is open-ended instead of a lot of what we see in the commercial space, which is scripted and linear and doesn't allow for errors. Once you're able to do that, then of course it brings up the questions of, okay, how do systems work with humans to make meaning or to make best the errors and mistakes that we all know are really important to learning? And the second part is, I believe, one of the largest barriers to adoption for XR is just the high cost of developing these experiences. And so how do we make developing XR like using PowerPoint so that teachers can make their own experiences in the future? Another example of a project that we have is, hey, we teach engineering design and manufacturing, DFM, in McE by having students take apart products all the time. That's great, but how do we actually scale that kind of pedagogy? Augmented reality is a really interesting interesting way because it's physically contextualized. It's also scalable, and you can publish it on things like Apple Store and Google Play. So we've now been able to do that over a number of different iterations of an online course, and now we're moving towards how do we gamify the learning? How do we bring in game-based analytics to hopefully identify, hey, are there patterns that novices might approach disassembly and making sense making of these different features and connecting them to design principles versus how experts might approach that kind of activity. And then this is one of the newer lines of work, and given that I know we have Mass Tech folks in the audience, the part of this was funded by the Mass Tech grant for advanced manufacturing, where Hollywood has been now in the space for about 4 or 5 years, where they're developing next generation green screen technology. So on the left, what you're seeing is snippets from behind the scenes of the production of Mandalorian. I don't know, raise of hands, any fans of Star Wars here? Okay, good, fantastic. So that was the first iteration of what we call virtual production now, basically taking high-density LED panels and turning that into the actual environment. So now when the talent points at a mountain, it's really there. It takes away a lot of the post-production costs, and it fronts it up so that now you can engage with it in a real-time way. It brings scalability and photorealism at a different level. So what you're seeing here on the right is we're finally developing the space here at MIT. It's in Building 35, again, partially enabled by support from Mass Tech. And now what we can do is how do we develop these beautiful videos and enable next-generation STEM learning? So if you're interested in that, happy to talk about it, but that's a new project in our group. And then finally, we're really interested in how do we scale both the learning. A lot of our labs are incredibly expensive in the equipment and also often underutilized. Like maybe it's only being used 1 or 2 hours in the day. Could we open that kind of up? So we have some work now in enabling teleoperations or developing teleoperations for students to be able to access really, really high-end equipment from a distance. And actually we have now a collaboration with University of Cambridge in UK to do some teleoperations across different tasks in manufacturing. So that just gives you a sense of the kinds of work that we're doing now in our group to be able to enable next generation learning and work in manufacturing. All right, thank you.
Thank you, John, Liz, and Dan, for your remarks and such an immense range of topics that all connect to the substrate of manufacturing and what it takes to get ideas out of the lab or the early stage to scale and all of the surrounding factors. So we have some time for short discussion, and then the iPad will probably have some questions that we'll try to tackle at the end. Let me start with you, Liz. I think at the start of your remarks, you said something like, the next 5 to 10 years will be the most dynamic time in manufacturing. Can you say more, or why you feel that way?
You want me to defend something I said?
I don't doubt it, but
my assertion. Well, I think that is. I say that for a couple reasons. One, I think just technologically, people who are, if you look across every field, really that it's touching manufacturing, that we're seeing these advances that were not even there, 5 or 10 years ago, whether that's in robotics or 3D printing or now with AI, what the transformation is going to be there. So there's a technological motion that now makes it possible to be doing things that we weren't actually potentially doing in the US before, and now we're seeing that, and we're seeing it globally, right? It's not, and so that on top of some of the other things I said. So for example, now with supply chains, people are saying we invested in our primary goal was efficiency in the last couple of decades for a lot of the offshoring of manufacturing, and now people are stepping back and saying, we have to also think about resilience on these supply chains. And so what does that look like? And part of that is domestic, increased production, but actually it's about strengthening global supply chains everywhere, and it's redundancy and it's regionalization, and it's also AI with predictive, optimization and things like that. So I think that's going on, and then we have this world order, shifting world order, which we see happening in terms of manufacturing and priorities and sort of alliances, a China-U.S. tension, and what does that mean? What are the implications for the rest of the world? I think are quite quite prevalent. And so I see like there, and then we have a policy piece in which the government, neoliberal models that said, we're just going to leave it to the market, are being pushed to the wayside, and they have been for a long time in other countries, in Asia certainly. But now we're seeing every country lean in to their investments in semiconductor production, in more resilient critical supply chains for critical minerals, which will have a manufacturing implication. So that that also just brings us into a time where everything is, it's a very dynamic time. All of the models that we were built on in the last couple of decades are really being, sort of upended, I think.
Thank you. And we certainly see in the companies we work with the interest in rapid change and these kind of pressures, or internal, external pressures that are causing reconsideration, and also, in my opinion, an interesting juxtaposition, maybe not entirely that, between the companies that are building new capacity, right? Take, John, you had a screenshot about Rivian and Rivian's new factory. Clean sheet, right? They can design it fully digitally from the bottom up versus, say, an established company that has to plumb new technology into its existing operations. And some similar challenges, some different challenges. And that leads me to you, Dan. So when we first met, I remember your technology is kind of magical, right? If I remember right, it's making something at a larger scale, not a huge scale, and then shrinking it down to achieve 3D patterning. Is that right?
That was what we did.
Okay.
And that's a lot of what happened at MIT. But then, you go out, you talk to the marketplace, and you hear what they actually need, right? And what we learned when we did that is that actually some of the biggest issues in the semiconductor industry is just getting things in and out of the chip, right? And this is the case for electronics, but it's even more so the case for photonics. And so having a material that you could co-package with these things in order to connect stuff together had become, and honestly always was, it's just worse now, the biggest pain point in the industry. So we actually switched to not shrinking things and using a scaffold material that consisted of glass so that it was compatible with these semiconductor processes. And that was a really critical transition and a pivot that we're very happy to have made.
Awesome. And building on that, can you talk more about the challenges you faced or challenges you anticipate facing as you scale?
Well, there's a long list of things, but as a scientist, it's not sort of these really hard problems you'd think about in science that worry me. It's sort of these like fiddly engineering problems of how do you glue things together 1,000,000 times? How do you position things with submicron tolerance over and over and over again? How do you make sure that your laser is stable and putting out what you think it's putting out day in and day out? So, I mean, these are the challenges you start to encounter when you're thinking about scaling up for manufacturing, which, of course, at these research stages are not so critical.
And I'm sure leading the company, you've thought about workforce and maybe the things beyond what you thought of doing your research. Yeah. What are some of the workforce challenges, or what kind of talent have you had to find?
The technologist thing is something that really speaks to me, right? So when we're looking for talent, the company is primarily not U.S. citizens, right? And that says something about the workforce that we have here. That's not by choice, necessarily. That's just what talent we have access to. But then you have to go out and you have to find people who are willing to take on more of the technician type role and things in between, like this technologist type role. And what we're finding is we don't find that in very many places. The way in which we've plumbed our educational system is just not fit to have both hands-on skills and this sort of analytical and creative thinking to solve these problems.
You can send someone to my program.
Well, but there are schools that are very good at this, and we should be using those as examples and maybe put trade programs together for that. University of Waterloo is a crazy wealth of talent, of people who have done co-ops at multiple different companies. So even in their second year in undergraduate, they can come in and start essentially doing all the things that we would expect out of somebody quite frankly, who's doing a PhD here at MIT, and oftentimes even better, they have even more hands-on skills. And that says something, right? There's something about the way we educate people where we have failed to really get them to do hands-on problem solving to an extent that is really important for these types of manufacturing problems.
So John, now I want to ask you the scaling question in a couple ways. Incredible impact already with the technologist program, like true congratulations. But 180 in a few years. What if I come to you and say, no, I want 180,000? How would you do it?
So we designed this to scale, and I would say this on a few levels. One is that the content that we've developed, it's meant to be done in a hybrid fashion. So there's part of it that's online, and then there's part of it that's meant to do in a hands-on lab. And so this is why we are partnering with schools. As you saw on the sites, there's technology centers in New England, there's community colleges in the region that we're working with, because skilled technical workforce, and this is one of the big differences, they don't often relocate for a job. Like knowledge workers do, but skilled technical workforce don't. They stay within the region. So in order to upskill a region, you really have to work with the regional partners there. And so in order to get to rural Massachusetts, we need an education site there. And so in terms of John's question, I'd answer this on two levels. One, the technologist program, if we're talking about that, it is meant to scale broadly, right? So once we have this blueprint with the 6 sites, now we have a full package where any education site in the US or really outside who wants to be able to do it can take up this package, send their folks to us for their instructors to be trained, and then they can launch TechAmp in their own site. And a lot of the lectures and the simulations are online already. And so sites can pick that up. We don't want to move away from the site nature, though, because of the regional connection. A lot of these sites are embedded with real relationships with their employers, many of the SMEs, for example, that Liz was talking about. And the second thing is, these folks, they're really hands-on, right? So we have to be able to offer those hands-on labs. The second part is, and this is why I'm so excited about the XR work that some of you in the audience are engaged with, that we're certainly supporting, is that, I don't think the technology is there yet, but there's a lot of ways to scale hands-on learning in ways that are scalable and intelligent that I'm really excited about in the next 3 to 5 years that, right now are still stuck in traditional modes of small cohorts, one instructor to 10. You have to be in the space right now. And this is why, I have schools coming to me saying, we have a wait list of 200 to 300 students every single year. We're turning away students from the trades because we can't get the capacity up. And so how do we work with those schools who are already in the space to be able to increase their capacity to get to the young folks or the incumbent workers or those who are underemployed who are interested in careers in manufacturing?
Yeah, I would just add, I know John speaks to this as well, but the other part of this is the pipeline, is how we're attracting the next generation into this field, because wages in manufacturing have not necessarily kept up. We've lost a lot of the wage premium we've had in the past. So to attract the next generation, we're going to have to also see, I think, if we can increase the productivity of these firms, they can pay higher wages, we hopefully can attract the next generation. But there's a lot of competition. If you look in Massachusetts, kids coming out of high school have a lot of options, and it's incumbent upon sort of the ecosystem broadly to try and bring that next generation in.
I think that's a good example of the kind of the marriage between technology adoption, productivity, and workforce, like with wages, right? You really have to tackle this from a lot of different aspects. Otherwise, firms can't pay enough, they can't get the right skills, they can't move into advanced modes of manufacturing, absolutely.
And John, I know you're thinking about AI these days and how AI can be incorporated meaningfully in education and learning. Maybe paint us a picture of 2030. How do you feel an MIT student will be using AI in learning, or how a technologist, a budding technologist, might be interacting with the platform in a way that's not yet possible?
Yeah, so I actually was just this morning talking to Sanjay. I think a lot of us know Sanjay Sarma, who's former VP of Open Learning and also in manufacturing, about this. So I would be really interested, even for the MIT student population, if we could move towards what is the future of human-to-human interaction for learning again. I think even from a faculty perspective, a lot of times we kind of delegate the teaching and learning to our TAs or to recitation courses. I think there's potentially a real way to recapture the one-on-one tutoring that still really is hard to compete against if you can think about a new paradigm, which is the teacher or the faculty as a high-end coach. Like if you think about an NBA athlete sitting down with their a coach or a trainer, usually there's a session where they're bringing out high-level analytics and covering the past week's performance and then thinking about a plan for the next week. Right now, we don't do that in education because it's so kind of costly for a faculty to spend that time. But imagine another generation of AI plus analytics to be able to inform a faculty on, hey, what is the student's progression in the past 2 to 3 years? And now in my 10, 15 minutes, we can really make that a very worthwhile experience when I'm crafting a learning plan for you in the next week that we're working on together. And so that would obviously require a new generation of AI plus learning, but there we're not scaling out AI to become less personal. It's actually recapturing the human nature of human-to-human learning.
I also want to emphasize that a big part of it should always be getting people out of the classroom. So much learning does not happen in the classroom. And you start to encounter the hairy problems in the real world, right? And that's the sooner you can get people doing that at a younger age, building, trying things, failing. And, in reality, this is kind of old as dirt, right? Apprenticeships. We should take those types of things really, really seriously. And that's just a form of mentorship. Right?
Yeah.
So we should really think about how do we bring that in a more meaningful way into all of our educational institutions.
That's a great point.
Yeah, great point. And one hope I have is this kind of symbiosis between the digital and the physical can make learning more of a continuum and things in parallel rather than maybe spend 4 years at a university and then go work. And maybe, like you mentioned, Waterloo, there'll be more universities with co-op programs. We see Northeastern, especially in mechanical engineering across the river, incredible co-op program and such capable students graduating already as experienced engineers. So to your point, definitely. Now, I will take us in a totally different direction, Dan. Foundries, vertical integration. Did you allude to, and share what you're comfortable with, like Irradiant will be the foundry of the future for these kinds of technologies, or do you think of how do you think of like that business model that?
This is a very complicated question. Yeah. The semiconductor supply chain, I hesitate to say I understand it, right? I'm just learning even. It takes years to even begin to get the map of what's really happening there. And more than that, different companies are vertically integrated to different amounts. So maybe I'm talking to, Google, and they vertically integrate down to here, but they also work with a supplier that's, in this window, and they work with an OSAT that's in this window, and it's a real mess. But that's also an opportunity, in a way, to do this sort of vertical integration. When you're going a little bit back to the drawing board, and you sort of have to do this to some extent, right? If you want to really do 3D nanofabrication, you have to solve the holistic problem. There's a chicken and egg problem there. You need the materials platform. You need the lithography. You now have this design space that nobody has ever operated in, so you now need the tools to design, and you then need to educate the market on what's possible in that space, right? And that's very, very complicated. To give you a more concrete thing where things insert really, really well, it's actually in advanced packaging. Right? So this is sort of one of the places we're finding there's a huge amount of pain right now. And essentially, when it's all inside the foundry, that's well and good, but then it starts to get very messy. So as much as you can, if you can take those advanced packaging steps in the semiconductor industry and turn them into something that looks more like a foundry process, you get a really big win.
Thank you. And I can imagine, while there's big challenges, however much you decide to own, that also is a big part of the moat, right? This is why manufacturing is hard. It's the knowledge of how to convert the design into the physical product.
Absolutely. And I think business model is actually a big part of it, right? You know, if we were a tool company, we couldn't solve this problem. If we were a materials company, we couldn't solve this problem. If we were a fabless company, we couldn't solve this problem. You know, you have to be all of these things when you're going from 0 to 1.
Thank you. Well, we just have a few minutes left. I shouldn't ignore the iPad because we have some questions from the audience. John, one of the audience members wants to hear about the Star Wars VR and how that relates to industrially relevant skills. It's not the highest votes, but I think it's a really cool question.
Okay. I'll give you an example. So I would love to use this, so I teach 2008. I don't know if this is an MIT person. I teach the yo-yo course, kind of manufacturing for juniors, seniors. This term we were totally oversubscribed. And one of the large limitations that we have is factory tours. Like, we're not able, I can only fit one factory tour in because we have to fit it within, class time. And then how do we transport, a whole bus load of folks, and can factories even take 70 students? Everyone is telling me no, they're only going to take 10, and then some of them, have restrictions and whatnot. And then when we're there, we're kind of at the mercy of the host. We might be seeing the process, 20 feet away, and we're kind of just listening to what the factory tour, guide is saying. They might not even be an engineer, and then the process might not even be active at the time. I would love to be able to, imagine if I had my own factory, and I could take students around and show them a process and say, hey, this part is incorrect. How do we do root cause analysis? And we can do anything we want to this factory. We can pause it, we can rewind it, we can go back to a particular place. Come with me. None of that is possible in a real factory. All of that is possible if I have a virtual factory that I can film myself walking around in a factory and do whatever I want with the factory. That's just one example. I think the mechanics faculty are really interested in hey, stress strain fields are really complex 3D. And when I'm lecturing, I'm just trying to take 2D cross sections. How do I lecture around this? Well, I'd love to walk through the field and do so. Or we have a physics faculty now working with us. She wants to rotate E&M fields for 802. She wants to rotate and rotate E&M fields and talk about it, zoom in and zoom out, walk through it, kind of I don't know if some of you grew up with the Magic School Bus, but you're kind of going through things and you're pointing out different features in a particular place. That could all be possible now with lectures, video lectures that we could do. Some of it for manufacturing, but potentially for all STEM at MIT. So those are just some examples.
Can we have a 3D virtual tour of MIT.nano?
Yeah, Vladimir, let's make it happen.
Okay.
Yeah.
Already in the future.
I will say one thing. MIT used to have this amazing program called Hacking Manufacturing, where they took PhD students and dropped them in factories in China, and then they messed around and saw what they could do with the manufacturing lines. And I would love to see more of that.
I had no idea. I got to find out about that.
Yeah, that's cool.
All right. That's a great way to end. Thank you again so much, and thanks everyone for listening.